Okay, so we can start. So this is the final lecture. We will try to wrap up diffusion models and basically the SDE part. So diffusion models based on SDE, stochastic differential equation. So for this, we need to know a little bit about ODE, forward and backward updates, and then we will go to the stochastic variant, and then we will see how it works for denoising diffusion models. So if you have not seen ODE, ODE, then we can have a quick review of this. So we can start with some recurrence. So recurrence, most of you know. So in this case, I obtain xi from previous xi minus 1. Okay, and delta t is fixed, and beta is, let's say, fixed as well. Okay, so obviously from this recurrence we will get updates, and so using this we will get update, but sometimes we may ask for certain recurrence, is there a continuous variant of that? Okay, so meaning at any not just only at the discrete points I will get the values, but I can give you value at any arbitrary point. Okay, so that's what we mean by continuous. So we will go there, we will derive that. So if you see here, then given a continuous time function xt, so here continuous again means that the t will be continuous. So basically it will take any real number. Okay, so we can construct we can have a delta t which is of length 1 over n, and so basically this is the discretization of the xt which is continuous. So xt could be any function, let's say sin t. Then sin t you may want to, if you have to discretize sin t, then you have to have multiple values of t, and let us say this is a uniform step length, let's say 1 over n, or the discretization step. So then in that case we will have n values. So we want to discretize xt, and let us say we have the time discrete components are from 0 to n minus 1 by n, and then and since delta t is 1 over n, we would like to know what is x at t plus delta t. Okay, so so here yeah, so this is how they are related. The new x plus delta t is 1 minus beta delta t t by 2 of the old one. Okay, so if we do some rearrangements, so we take xt on the left, okay, and divide by delta t, then as you can see, this we have on the left hand side xt plus delta t minus xt by delta t, and on the right hand side obviously we have minus beta by 2 xt. Okay, so we did some rearrangements. Now from here you can see that if I take a limit delta t tends to 0 here, then this is very familiar. If we have a function f t plus delta t minus ft divided by delta t, and delta t goes to 0, this is exactly the definition of derivative. Okay, so this is what we will do. If we take the limit, as the limit delta t tends to 0, this difference equation becomes dx by dt. Okay, so that's what we know. This is like derivative of x. Okay, so we wrote this left hand side as dx by dt, and right hand side is minus beta by 2 xt. Okay, so so what we observe is this recurrence relation that we have has a continuous variant like this. Okay, and the solution to this should give me same solution at the discrete points here. Okay, so this is what we call from discrete to continuous. Okay, and why this matters for diffusion models? Diffusion models, as you can see, the way you propagate your xi, they follow certain recurrence relations, right? We will make that precise, but this is how they are. Okay, so the idea was, can I see this as a continuous variant? Okay, so if you do if you kind of work in areas like natural sciences, then this type of differential equations are kind of good models to explain quite a few things. Okay, so even in physics you might have seen some of these equations, right? So, and if you go into very sophisticated models, then for almost everything except for few things in physics, we have differential equation models. So if you want to know electricity and magnetism, then you go for Maxwell's equations. It's the differential equations. If you want to study fluid dynamics, then you have Navier-Stokes. If you want to study usual diffusion equations, wave equations, all these, there are differential equations. If you want to see propagation of in quantum mechanics, then you have Schrodinger equations, and so on and so forth. Okay, so these are physical world we believe is continuous, and we would like to kind of describe it via a differential equation. Okay, so that's the connection that these guys saw, that looking at this recurrence, perhaps we could model them as some continuous form. Now, why would one like to do that, right? So that's the first question. If I can solve my problem anyway in a discrete way, it's a simple for loop, then why should I do that? Well, in some cases, if you are kind of lucky, then for example, in this case, the solution is kind of in closed form. Okay, so in this case, the solution is just xt is e to the minus bt by 2. So it's one sort solution is there. Okay, so of course not for all complicated recurrences you will have such nice closed form. Okay, so so this is one of the things. So now look at forward and backward. So what we saw here is that we are looking at the forward case, right? So we are thinking as if the time is increasing, right? So we are saying what is the rate of change as the time increases, right? But you can ask the same question in other way, right? So when we take derivative, we are kind of like looking at forward difference, right? But then we may also talk about the other way. So this is giving me propagation of xt in forward in time. But there is also a reverse process, right? So we may ask same question now, can you have reverse one? Okay, so then yeah, so we have the forward one, and if you would like to see gradient descent, then gradient descent recurrences are like this. Then again, by doing the same way that we did before, this will be given by dx dt minus beta delta grad fx dt. Okay, so I mean here you can take beta I to be some beta delta. Okay, and then you divide by the delta t, and then take the limit delta t tends to 0. So then it becomes like this. Okay, so essentially gradient descent is also can be seen like this. So so in this case, if you want to see, so in gradient descent, yeah, I mean how is your x propagating is kind of given by gradient, right? So what does gradient descent do? Gradient descent takes you to the point of minima of a function, right? So here your guiding force is this gradient field, right? So if we plot the level curves like we saw in the last class, a 3D function, we could kind of see them as level curves on the 2D plane, and if somewhere there is a minima here, then gradient descent kind of goes like this, and it goes towards the minima. Okay, so this is the gradient field that gradient descent is following. So at any point xi, we are looking at the gradient, and we are following negative gradient because we want to minimize. Okay, so this is our guiding principle, right? So this force fields kind of force you in towards something, right? So gradient of f as such is one possible force field that is pointing at here is telling me go here, here is telling me go here, here is telling me go here, like this. Okay, so these are the vector fields, right? They are like this. Okay, and this is creating this drift that I'm looking for. Okay, so we will try to make this general. For SGD, we want to follow negative gradient direction because we know that negative gradient points in direction of decrease, and if we keep following negative gradient, then we will go to minima. Okay, so as such, this has general meaning. This is a drift term. So depending on the drift term, you will be forcing x to go somewhere. Okay, so So this is our recurrence for the forward case for SGD. Then new xi is obtained from old xi, and let's say the additional directions that I get via gradient descent is given by del xi minus 1. So in this case, it's exactly this term, del xi minus 1 is this minus beta I, which is treated as step length in SGD, right? So or here we are talking about GD, not SGD. There is no stochastic term right now. So this is the update, and this is the way update happens. And if we now have to do the reverse case, then obviously I will, instead of like plus delta, I will subtract delta xi. Okay, so basically, if I do that, then the plus here we had a minus. The reverse process would be plus. Okay. So this gives us the intuition that in this case I should follow the grad negative gradative direction or positive gradative direction. Okay, so these are forward and backward process here. Let's move into SDE, okay, stochastic case. Now we can have similar discretizations. Xt is a continuous, and interval 0 1 could be divided into n steps. Let's say I over n. This can be readjusted. Interval is not a, I mean, for simplicity we take this, but okay, so xi, the way the notation is, the discrete xi will be x computed at I over n. Okay, so that's how we see the discrete version, and xi minus 1 will be x computed at I minus 1 by n discrete point, and time step is 1 over n. Okay. So as you can see from the previous case, we have just this extra term here, which we call which is a finer process, but otherwise everything is similar. Okay, this is like the SGD update. So Wiener process, the ZT itself is defined like this. Okay, and ZT is difference of W t plus delta and Wt. So ZT itself by itself is, I mean, W itself is not a Gaussian noise, but the Z is a Gaussian noise. Okay, so ZT is defined as a difference of these W. Okay, so the way it is written is like this. So this is the way to formulate stochastic case. Okay. So in the continuous variant. Okay. So we can write like this. Then from here we can divide by delta t both sides, and so then we get dx by dt, and tau also we can see as tau delta t, and zt we can expand it like the difference here, and then again we can divide by delta t. So let me do this very quickly. So from here we have xt plus delta t minus xt, and this so I took the minus delta t, and then let me do one step. So minus tau like with a little bit of abuse of notation, I can write this as tau delta t grad f xt, and plus zt is d, or let us write like this. Okay, w t plus wt. Okay, now I can divide by delta t on both sides. So I divide by delta t on both sides, delta t. So this goes away, and there is a delta t here. Okay, so overall what I get is this is so this is dx by dt. Okay, and now I take delta t tends to 0. Dx by dt is equal to minus tau grad f x, and plus w and t plus delta t minus w t by delta t, limit tends to 0. This is defined to be dw by dt. And now if you multiply by dt on all sides, then you get this. Okay, so dx minus tau grad f xt dt, because you multiply dt on all sides, and then dt also goes away from here. Okay, so this is how we go from discrete to continuous. The way Wiener process is defined, we use this fact here. Okay, so now we get to the continuous variant is written in terms of dw. Okay, in the stochastic case. So this is the continuous variant. Now, if this is the forward diffusion, okay, so if the diffusion is defined like this, then fxt and g has some physical meaning. Okay, so first one we call it drift coefficient. Okay, so the way you define the drift. So in SGD case, it was negative of the gradient. Okay, we followed that. So physically, it could be like how molecules in a closed system move in the absence of random effect. So this is usually seen in Brownian motions and things like that. Okay, so they are defined like this. For GD, drift was negative gradient. So basically, this drift forces in the GD case, it forces the solution trajectory to follow the gradient of the objective. And GT is the diffusion coefficient. Okay, so it describes how the molecules would randomly walk from one position to another. Okay, so the drift is like the overall on average where the behavior of these molecules in the case of gradient descent, on average it will go to the minima. Okay, there is a randomness, so that's why we say on average, and the diffusion is like how much kind of fluctuations it's going to do. Okay, from one position to another. Okay, how much randomness will be there? It will be a zigzag motion in the case of stochastic gradient descent. If you plot stochastic gradient descent, then it converges like this, whereas GD converges like this. Okay, so this is what we are talking about. On average, the amount of randomness it has while it goes, but overall the drift is forcing like this, right? So if it is negative gradient. Okay, so SGT convergence is pretty much analysis also is done like this. Okay, you do the expected thing, right? So you expected f star minus fx. So this determines how strong the random movement is. Okay, so basically from here to here, each step, how much fluctuation it will do. So one possibility is that on average it goes, but it goes more like this. Okay, so that is determined by this GT. Okay, the diffusion coefficient. So if we look into some simple examples, this is a very simple example of a diffusion equation, but you can see the drift term is missing here. So you have only the dw term and some a is there. Basically GT is a here. So and then in this case we can write the iterative solution, discretize this, so which is very simple. Dx is xi minus 1, and a is a constant, and dw is wi minus 1. So and wi minus 1 is a Gaussian process, so Zi, right? And if standard normal, let's say. So if it's standard normal, then this means that each time from algorithm implementation point of view, each time you have to sample from Gaussian random. You will start from initial x, okay, x naught. So in this case, initial x is 0, okay, and alpha is chosen to be 0.05, and number of time steps you will do is, let's say in this case 10,000, and Zi that you have each time, the amount of fluctuation that will happen one step to another is determined by standard normal in this case. Okay, so we call this numpy library to sample, and then we just follow that iterative process defined by this. Now if we plot this, then this is how solution to this diffusion equation is given by this plot. Okay, so sometimes you see some stock prices also behaving like this, right? And this is the reason why stochastic process is very popular in quant jobs. Okay, they have this kind of stochastic processes. Okay, they study a lot of other models, Black-Scholes model and things like that. But yeah, but essentially SDE is one of the central tool in those jobs. So so we only had diffusion term here, and we had a simple code. Now we can make it a little bit different this time. So we have also some drift term involved, which should follow minus alpha by 2 x, and we do have the usual diffusion term. So if we the iteration is pretty much similar. So if I plot this now, and I have implemented this iterations after discretization, which is written here. Zi, yeah, there is a mistake here. Should be Zi minus 1. Okay, so this is the Zi minus 1. So again, it is random normal, standard normal, and yeah, this is the plot you see again here. Okay, this is how this evolves. So right now there is no physical meaning to these things, but many real life problems are modeled like that. But we will see. In our case, the real life problem is the diffusion model. Okay, so so we have seen. If I go back a bit. So if I go back a bit, then so this is the forward diffusion. Okay. So we remember this because in diffusion equation, diffusion model, we have very similar forward diffusion. We will make it precise. Then there is a theorem by Anderson that if you have forward diffusion defined like this, then the corresponding backward diffusion is. So here, here is the reverse one. Okay, we are not going to prove this, but we will take it. Okay, it was proved long time ago, 1982, that the corresponding backward one for that one, because for different one it will change. Okay, of course you have liberty to have f of your choice, and you will plug in the reverse case also, and it will give you the backward diffusion. Okay, so this is backward diffusion, and so now in the backward diffusion, as if you are going a time reversal, right? So you want to trace back the way you came back, right? This is not easy as such, because the way you went forward was with some random perturbation, right? And you're trying to kind of reproduce the track. Okay, but on average you want to kind of reproduce as much as possible, right? So while the backward process, the drift term now changes like this. Okay, in the forward process, drift term was fxt only. Okay, now you see this log term also, right? Log pxt. Now we have seen log pxt in the last class, ptx, right? This came from Tudy's formula, and in Tudy's formula, we said that we substituted the x naught in the true denoiser, and then using Tudy's formula, we somehow got this log term, and then the approximate denoiser just had to kind of learn to predict this so-called score. Okay, so this is the ground truth score, and then it came up with s theta to predict this. Okay, and somehow you see here it is showing up again, right? So this is grad log pst. So this is how they are connected. We will see this, but from abstract point of view, for the forward diffusion we had, this is the corresponding backward process. Okay, reverse process. So everything is kind of known. GT is known, f is known, provided you can compute this grad f log ptx. Okay, so if you can do that, and so example of a reverse diffusion would be let's say if I want to solve this reverse in time, then obviously my iteration would kind of reverse. So now I'm supposed to get xi minus 1 from xi. Okay, so that's how the reverse process happens, right? So I can do that, and w will also be reversed now. So wi minus 1 minus wi. Okay, so with this we can write the reverse process as well. Okay, iteratively. Now now we had a background on ODE. And forward process and backward process. We also did a stochastic variant for the forward process and the backward process. Now let us put all these ideas for DDPM, the denoising diffusion model. So let us get into some notations first. So delta t as usual is 1 over n. Beta I, we write it as some beta computed at I by n. And overall it could also be written like this: beta t plus delta t, and xi is x computed at I over n, which could also be seen as x computed as t plus delta t, and zi also will mean z computed at I over n, or z t plus delta t. Now this is how we were propagating in DDPM. So this is just another recurrence relation. Now from what we have learned in previous slides is that this recurrence can be formulate this as SDE. Okay, so from the discrete case, you can guess that this seems to be your so this is your diffusion term, right, and this is your drift term, right. So this is the discrete variant that we know. This is how we were propagating x in the forward case for the DDPM, right, xi and from xi minus 1, right. So this we recall, it is just that now we are using beta in place of alpha. Okay, there is a slight change of notation. So with that we had this. So this is our starting point of forward process. Now we will do a lot of simplification and get to this continuous variant. Okay, that's our objective. And once we get to continuous variant, what is the objective? We can use some SD solver. Okay, well-known SD solver, because these are kind of well studied. So maybe we can just leverage those solvers. So that's the point. So from discrete variant, we do some simplifications. So basically beta we put the notation of beta. I think there is a little bit of a error, it seems to be here. I think we can ignore this safely because anyway, if it is correct, it's fine. Okay, I believe this was beta computed at I over n. Okay, so this seems to be, so even if we ignore this, it doesn't hurt. We can directly look into this. So what is x at t plus delta t? This will be 1 minus beta t plus delta t. Okay, that's coming from here, and then we have xt. Okay, so the way beta is defined is like this, right? So we just have to look here. Okay, so beta we substitute it like that. Okay, and same thing here. We have same thing is done here. Beta I is replaced by beta t plus delta t, and z I minus 1 is nothing but zt. Okay, because zi is zt plus delta t, and zi minus 1 will be just zt. Okay, so you agree with that? So these are some simple going from discrete to continuous and so on. So now in the next step, we did some approximation here. Okay, so if you see this, the last term did not change. Okay, so there is no change here, but you will see this changed coming from here. So what was the change? So this we did some expansion here. So this is of the form 1 minus x to the half, and this is written like 1 minus half x plus, and then some I guess x square term or something. There is a expansion for this, right? So those expansions. So basically we kind of ignore the higher order term. Okay, so that is being done here. Why we can ignore those higher order term? Because those higher order term will be involving some square of delta t. Okay, and delta t, as we know, we will be taking delta t to be quite in the continuous case, delta t will be getting smaller and smaller. So this is okay to kind of drop the higher order terms. So in this expansion, I will just take first two terms. Okay, so that's how we have only first two terms are there, and higher order delta t square terms, cube term, and all this is believed to be insignificant here. Okay. Okay, and then we did a simple kind of multiplication. So xt goes inside, and then here xt goes inside. That's all. We had beta t plus delta t. It seems we also did one more approximation, right? Because it seems like Taylor approximation of beta t plus delta t also was done. So beta t plus delta t is beta t plus beta prime t delta t and so on, right? So this is the Taylor expansion we have. So we did this further approximation here, that we had this first term only of the Taylor expansion. Okay, and then this this delta t is already there, because you know, if you do Taylor expansion of this, certainly delta t will be there, but there is one delta t outside as well. So that delta t multiplying again will make it second order in delta t. So by the same logic, previously we already removed order of delta t square terms, and this guy will also become order delta t. So basically we keep up to the first term, and then delta t we just keep wherever only delta t is there. The moment delta t square starts coming, we throw away that, right? So all this is fine, and then again we did the same thing here. Okay, t plus delta t, we did Taylor expansion, so we got b of t plus b prime of t delta t. But then that delta t and delta t, again same logic, right? So we throw away that. So we just keep the first term and then this guy. Okay, and all this is provided beta is well behaved and bounded and so on, right? You may say that delta t square is kind of will go to 0, but what if beta t sharply rises, right? So there is a few things that we are assuming in the background, right? Or what if your beta t was so high that it negates kind of delta t square, so it is still significant. That's what we are trying to say, right? So can you throw away that in that case, right? So the underlying thing is that you assume that beta is kind of not changing too much. Okay, beta t was kind of I mean, if you study PDE and so on, these diffusion coefficients obviously play a important role, so they should not be jumpy basically. Okay, so let us keep things up to that point. So so we did all this, and we have this. Now we now basically we want to go from here to the continuous case. Okay, so basically we move this guy there, we divide by delta t throughout, and then we should get this basically. Okay, so if we divide by delta t, so xt plus 1, xt plus delta t minus xt, right? And then we divide by delta t. So when we divide by delta t, this goes away, right? Here the delta t is in the the way beta t delta t is defined, it will be beta t, right? Beta t delta t is like this, right? Or it will be like beta, the way beta is discretized is like this, right? So this will be beta, and zt we write it like w t plus delta t minus wt, and then we divide by delta t here as well. Okay, right? So that works out, right? So so this will be kind of dw by dt. So because we divide by delta t both sides, right? So this is our left hand side, and this is our minus half beta t, delta t went away, and plus this guy here, okay, which is z is difference of w, and this came after we divided by delta t, right? So all this comes out to be like this. Okay, so basically this is like dx by dt is equal to minus half beta t and plus square root of beta t, and this was dw by dt. Okay, from here dw by dt. So now we multiply by dt on both sides, you will indeed get this, right? So this is how we go from ddpm discrete to ddpm forward diffusion case. Now from here you can use those formula, right? So this is your f xt, right? So this was your f xt, the drift coefficient, and this is your diffusion coefficient gt. Now you can leverage on SD theory, and now you can say, by looking at this, now I can immediately write the backward diffusion continuous variant, right? So we can write down the reverse one now. So we derive the forward one, and with that abstraction fxt gt, we know that from the Anderson's result, this is the reverse one. And in the reverse one, with our choice of f, our choice, or like this came from the diffusion process, ddpm discrete process we arrived at the continuous process, and from the continuous process we read out what was our f and g, and that f and g has to be substituted here, and this gives you the reverse process basically. Okay, so overall this we will get into this reverse continuous diffusion process. Okay, so again if we do the discretization and so on, so dx as usual, this is the reverse process thing. So then yeah, so we do the usual discretization, and dt is replaced by delta t and so on, right? So and then xt minus 1 we write like this, xt plus and so on. We just send this xt on the right hand side. It seems nothing has changed. And then we take xt common from here and here. Then we have this guy, and beta t got multiplied here, so this is all fine. And then we have an approximation. Yes, so this approximation is this guy. We artificially added one delta square t term, because we know that delta square t term will be insignificant, but it will help us in kind of formulating using this later on. So we added and subtracted delta t square here, but everything else remains the same. And then from here so we take this 1 plus beta t delta t by 2 common. Then what do we have? And this is same. The changes are in, okay, there is xt here. Okay, now I see. So 1 plus beta t delta t by 2 we took. Then there is an xt term there, and we have beta t delta t plus this term, right? So there is this one xt one. Yeah, it seems to be. Yeah, it seems to be okay. Okay, so that's fine. So if you do this, if you just combine this term, okay, if you combine this term, then this is this term. Okay, so you can verify this, right? Or basically not just that, all this, all three. If you combine all three, so sorry about this. So if you combine all three and simplify, you get this. Okay, so we have combined all three as this guy. Okay, I hope you can double check. It seems to be working fine. Okay, and the remaining term is this term here. So from the discretization scheme we had, now we can write down xi minus 1. Xi minus 1 is our xt minus delta t. So we can just substitute those discrete values. And then 1 plus beta I by 2. So this is beta I by 2. Then we have xi plus beta I by 2 and so on. So this we have xi plus beta I by 2, and then this the discrete variant of that, pi xi, and then square root of beta I zi. Okay. And then we did an approximation of this via this. Okay, because this is like 1 minus beta I to the minus half, but this is approximated like this, right? 1 plus beta I by 2. So so we are here basically. Okay, the discrete values could be written like this. So this corresponds to the backward process. Okay, so we came. So what did we do so far, right? So we started with the forward process of DTPM, the exact DTPM, and we got to the continuous variant of that. The continuous variant of that we have we know the continuous variant of have from the continuous literature that there is a corresponding reverse one, and from the reverse one we the continuous one we came back to the discrete one. So we are kind of trying to go from discrete to continuous, and then also from the reverse we want to see what could have been the possible discrete for the reverse. Okay, so this is what we are trying to kind of do all this. So Song and this they call this reverse this way of computing the reverse as variance preserving SD. So they were the one who kind of introduced this SD variant. So the idea is now if you have these continuous variant, right, forward and reverse, can you not use some existing solvers? So we know that for ODE we have the popular Euler method. To solve this ODE, then there are like, if I have ODE problem like this, then I can indeed use Euler scheme and solve this, right? And this, as you can see, is analytically also kind of exponential. And there are other variants of solving these. So basically the point here is the basic forward process that you do and the basic reverse diffusion process that you do, it is just one type of discrete scheme. But when you saw the continuous variant, then you say, oh, okay, now it is a continuous SDE and there is a rich literature of not just one type of recurrence to solve that. I can employ a variety of interesting solvers. Okay, although you will be solving iteratively, but the fact that you could see this as ODE and continuous variant, there is a literature. So for example, Rangakutta method is a fourth order method. So now it's not like you are bounded by just one type of iterative scheme. You know that this is a forward process, you know that this is a backward process, then why not use some even better iterative scheme? Okay, so this is fourth order, and it is usually much better than Euler method that we have right now. Okay, so this is kind of settles the SDE part. So what are the applications basically of so I'm using these slides. There's a nice 3-hour video lecture in CVPR as a tutorial. Of course, they don't go into the detailed maths that we do, but from application point of view, they have discussed quite a lot. So now from engineering point of view, as we saw in VAE, in GAN, basically it's about a lot of playing around with architecture and so on. So if you remember, the forward process, usually we don't use any neural network. It's nicely scheduled via signal to noise ratio, and then it is your choice how you want to bring down the signal. So you choose some monotonically decreasing function that decreases the alpha, and there are many variants again, right? So but that's not an issue. Okay, so there is this, some scheduling could be taken, and we get to the pure noise. And then from there, the denoiser is the heavy lifting part, right? So denoiser has to, at each step, kind of try to do the reversal of denoise basically, right? So then the denoiser architecture, what you will choose, okay? Because again, it's a neural network. So here a lot of engineering will go in. You choose your UNet, you choose your ConvNet, you choose a transformer, and so on, basically. Okay, so which one works? You have to play around a bit and see which one works. There is no like theoretical guarantee or something like that. Okay, so UNet, as you know, UNets are like this. It's a kind of a ResNet. The difference is like it does a concatenation of the conv blocks here. Okay, so these blocks get concatenated, but then as I described in the previous classes, these concatenations could be also formulated as a kind of a residual thing. Okay, so so this is UNet. It was proposed for medical image segmentation, and that's where it became very popular. It's perhaps the second highest cited paper after ResNet. Okay, so it's become so popular. So you may throw in denoiser as a ResNet. I mean UNet. That's it. Okay, and then each time you are kind of trying to do the denoising step. All this fits in the basic algorithm we have. Now one more thing, what you can do, you can do conditional generation like you have done for GAN, you have done for VAE. Now you can have some conditions thrown in here. It could be some semantic map. It could be text. It could be representations and so on. Okay, so one could have conditional generation as well. Okay, so because anyway it is supervised training, right? So it is end-to-end supervised training. So image goes in, and then this gets mapped here, and then you will append a conditional thing. So you say, yeah, I want to generate, I will sample it from here, but then I have some additional condition here, which will be also encoding of some text or something, and then you will say, okay, the input image that went in was cat, I'm going to append that class level, and then the reconstructed image should be cat only. Okay, so that way you can always kind of put the condition in. Okay, so we have seen this before. So conditional generation is pretty much doable, right? So this is engineering, right? You throw in this, you throw in some conditions, that's it. Okay, there is no maths doesn't change anywhere. Okay, so these were some popular results. As you can see, these papers are quite new. Diffusion models themselves are quite new. They came around like within 3 years. So there were this ImageN, I believe from Google, and stable diffusion from stability, I guess, and then EDIF. So these were the papers proposed based on these UNet architecture. Okay, so these are the another opportunity is to use transformer. So transformer, as you know, is usually used for time series data. In the beginning, it was proposed for text processing and so on, and that's also in the ChatGPT now. So as such, we believe that this is like for sequence thing, right? So I put in a lot of text, and then sequence of texts get processed, some attentions are given and so on, and then it can do any text-to-text kind of processing. But then later people figure out that images, why not we kind of divide them into patches, and then treat them as a sequence. Again, this sequence, I mean, images. Sometimes we feel, okay, does sequence matter? But in abstract sense, we create some patches and then let it figure out which patches it's like a jigsaw puzzle, right? So which patches, it will already figure out, okay, where to put this attention in these patches and things like that. Okay, so they went with this very abstract idea that take images, just create these patches. These patches are like words, and then just put as it is without changing much in the transformer, basically. So this is the vision transformer that was proposed here. So this is the processing you have to do for images, kind of make it into small chunks like words, and then now you can use this again in the denoising step. Okay, so given an image which is a slightly noised image. Okay, so let us say at xt some noise was added, and the transformer is supposed to predict the noise. Okay, so let us say we go that with the variant where we had to minimize epsilon hat theta minus epsilon at t, right? So the noise that was added at the time step t, the transformer is now trying to predict the noise. So this was the noisy image at t, or the epsilon t was added here, and then we are trying to predict the noise that was added. Okay, so we will train this network at each time step. At t+1 you will add more noise, and then the transformer will try to predict the noise added at t+1 and so on. So this way it will get trained. Okay, because as you can see from the training, DDPM training, we can sample t from 1 to t. Okay, and kind of train like that. So again, the main thing here is again engineering, right? Because the overall idea is anyway known, but the way you will do now is that you will use transformer. You will create patches, you will pass it through vision transformer like this, and just use it as a denoiser. So with transformer architecture, these were the papers that were proposed, and they indeed improved quite a lot. Okay, with transformer. So the first one is with scalable diffusion models, and then this is, I believe they did it for multimodal, although I don't know the detail of this, in which way it was multimodal. Here, it may be because of text to image, right? So in that way, maybe it's multimodal. Okay, so they seem to be giving caption, and then the images are generated here. So again, all are using transformers. Okay. Yeah, and I believe this is for high resolution. Okay, so these are kind of pretty recent papers. Now, image editing, just like latent space engineering that we were thinking about, so can we do some kind of editing, right? So we saw drag GAN, we saw go GAN. So we just create sketch, and then it does that. So those were pretty nice. We could figure out with GANs, we could figure out with VAE also to some extent. So, but is it possible with diffusion models, right? So that's the point. So can I do this fine level editing? So for instance, I have this idea, a sketch in my mind, and then I want to generate some image, and that should look faithful. Okay, so so if input is this, and then if it produces this looks good. Okay, but if it produces like this, it doesn't look that good, because usually we associate clock towers as kind of independent big tower. Okay, usually it's not in residential kind of area. So these kind of problems they looked at, what is kind of realistic and what doesn't look realistic. Okay, so so this is one thing. So your input could be some segmented image or kind of sketch, and then you would like to generate some realistic things. So again, this could be seen as conditional or guided generation, right? So this is the SD edit paper. So guided image synthesis and editing with stochastic differential equations. First perturb the input with the Gaussian noise, and then progressively remove the noise using pre-trained diffusion model. So this was their idea. So your input was this. Then first you perturb this up to the Gaussian noise, and then progressively you kind of remove the noise using pre-trained diffusion model. So basically they use this pre-trained one. We don't know when we say pre-trained, then how, I mean, on how many data it was pre-trained, right? Because if it has never seen something like this, will it still be faithful? Okay, so these are the things one can only know after playing and going to detail, right? Because the data set it was trained on, things like that. There are so many things. So if they say pre-trained, it must have been pre-trained on quite a lot of data that could resemble some realistic pictures like that, right? Okay, so so these are the fine grained control by SD edit paper, that you can have this, and then it can produce this. So it can go up to some very noisy, let's say standard normal pure noise maybe, and then from pre-trained they could generate this. Okay, and then from this, I guess, they go to this some noise, and then they use this pre-trained to generate this. Okay, so these are the editings they could do. They could also do this via stable diffusion as well. So you can have this this sketch drawing, and it would try to produce this kind of realistic looking image. Okay, and yeah, image composition. So some of the things we saw this before, that especially with StyleGAN, that we could play around with the features like hair color, or in this case even you can put some glasses on, right? So StyleGAN also kind of this is possible. You can have picture A with glasses and picture B with not, and usually it does. You can put on glasses there. So it's possible, and here also they could do this kind of findable color change and put glasses on and so on. So these are the editings they could do with SD. This is the same SD edit paper. Yeah. So idea for them is kind of similar. They again go to this latent, and then they try to regenerate again from the pre-trained one. So these are again for conditional generation. So this is another paper. But in this paper, what they claim is that you may define some very restricted area in the image, and it may try to kind of create cloud. So you are indicating this area, then it will try to generate a cloud there. Okay, and you may indicate an area somewhere here, and it will try to kind of fill this with this plants or something like that. Okay, so this is like you can indicate the regions in the image, and it will try to kind of generate those. Okay, so they claim that this is kind of their approach is like very fast, and they could do in much less milliseconds and so on with this specific regions of editing. Okay, so I encourage you to read this in detail. I have not read some of these in detail. So it's better to always check the paper. Okay. Yeah, and there is also like DDIM inversion method that was proposed, and that also helps in this latent space embedding, like so. So it can go from the style of this tiger to generate the style of the cat. Okay, so obviously you have to give this class condition cat as well, and this guy is getting mapped to some noise, right? But then from here onwards, if you have some class conditions as well, then which is cat, let's say, so it will take something from the noise embedding, let's say, and with the class condition that it is you are trying to generate a cat, it will try to kind of generate the cat, but it will preserve the overall thing, right? So the pose of the tiger and everything kind of gets preserved. It just is supposed to kind of change the class. Okay. So these are kind of editing it just. So one can kind of do style transfer also. Okay, like we saw in the style GAN. So here also it's possible to do multi-domain transfer is possible. So all this with the same kind of pose. I'm not sure about this, but here they look all kind of same, right? Here also you can transfer the style. This is your reference image, which is the style. Style meaning it is like there is a lot of, it's kind of a winter and ice and so on, right? So can you kind of transfer that style in the source image 1? Okay, so this is something style GAN was doing, and here also it's possible to do this kind of style transfer. Again, going back to not going back, this is a new one, diff edit. So that was SD edit. So you can semantic image editing you can do. So basically here, let us say the input image is this, the caption is a ball of fruits, and the query is a ball of pears. So can you do that? Right? So this is not very easy problem, right? So you are given a reference image. Now there itself you have to change some things that I want. So here it's a ball of fruits, but I only want a ball of pears. So the things that the model should learn is where are the fruits. So basically some form of masking it should learn. Okay, so intermediate representation should be the masking. So where are the fruits? So these are the red ones, these are the fruits. Now after you have located those fruits, you will fill that only that part with pears. Okay, so same here, a ball of fruits, but then now you are asking about a basket of fruits. Now it is supposed to identify or mask the basket, which is the red thing here, and it should replace that by the ball by basket. Okay, so this is kind of a very good amount of control you have, right? You can change specific things in an image. So this was proposed by diff edit. Again, this is a diffusion based model. You may read this in detail. Again, the same process we may want to do here. So problem is that horse is there, and I want to transfer this to zebra. Okay, so again your query would be zebra, and the reference is horse. So now the model will do the masking. Where is the zebra? All this should happen kind of end to end, right? You don't have to get involved saying that this is the horse, right? It should be automated. So this is the mask that you found, and then through these steps, again it should go back and create this, put a zebra there. Okay, so yeah, so this is also from diff edit. You can change I guess the guitar and specific objects. Okay, this is another paper, imagic text based real image editing. So again here there is a target, and text is, this is the bird, and then you want bird to spread the wings. Okay, so now the bird is spreading the wings. This is the input image, and you want this to change to a person giving the thumbs up. Okay, input image, and then the goat jumping over the cat. So this should change to this. Okay, so they are like given an image, what level of editing you can do. Okay? These are the things. So this is what is proposed by Imagic. They kind of have an intermediate, because this is kind of text guided, right? So it is text guided in the sense that given an image, you want to edit the image via text. So there will be some form of text embedding as well to understand what is being asked. So this is the text embedding optimization that they are doing, and then finally the fine tuning of the model, and then the final prediction they have. Okay, so you may look at the specific details of all this a bit. Yeah, so specific details, I encourage you to kind of look at the paper. These are mostly engineering type, like they have this target embedding, and then they train the optimized embeddings and so on, and then finally they could interpolate. So they know a reference embedding, and then they know the target embedding. So between that, by interpolating, just like the latent space embedding that we were doing, we could have these kind of editing. Okay, so yeah, so look at this paper. I'm certainly not going in explicit details. These are the things you can do. Okay, photo of a dog, tree color gets changed with autumn leaves. Dog, you can make it sit, right? So this we have seen. This we have seen the horse now raising its head. Okay, so all this kind of editing could be done. Prompt to prompt image editing with cross attention control. So this is also image editing paper last year. So so basically, given a prompt, and let's say you generated something, but then for that itself, you just want to change a little bit. So photo of a cat riding on a bicycle. Let us say you generated, right? And then, but then you want to kind of remove bicycle and change it by a car. Okay, so landscape with a house near a river, and then maybe you forgot something, right? So given the same image, because if you try this in DALL-E, right now it doesn't do that. Okay, so let's say you asked DALL-E to generate an image, and then you ask that in the same image, can you have a rainbow in the background? It will not do that. It will generate completely new image for you with the rainbow in the background. House and everything will change. So in that sense, these are interesting. For the same image, I just need few other things maybe I forgot, so I added this. Now if you add something like that, right, later on you change the word, you added something, so how will you do things like that, right? So you forgot to put the jelly beans, right? So and then this kind of thing, right? So what they propose is that the architecture that you use, let's say if you use transformer architecture, you can read about transformer architecture, it's not that complicated. So what they say is that in transformer architecture we have obviously we have kind of multi-layered thing. You have a key, query, value kind of thing. So but all this you do this q, k transpose in the transformer, and then you have attention maps, and then you do some kind of a cross attention there. Okay, so this cross attention that you do there itself, you can do some edit. Okay, this is their proposal, and this is what is working, we saw. So what they're saying is like here itself, if you can do some editing, like the word swappings and that you have, or adding a new phrase. So maybe you have some of these more here. Or you can even do the attention weight weighting. So basically because it's a form of a linear combination here, so maybe increase attention weights of some of these artificially by yourself, and that might create some interpolations between these and the output will get changed basically. Okay, so this is still high level, I agree. So you have to work in these this cross attention layers. Okay, and do some changes there. Okay, so corresponding to the text, and I believe it is corresponding to the text, and which texts are getting more attention and things like that, and based on that you have to do this. So yeah, so this is one thing. So one can do latent space in the cross attention layers. So these are the results from there itself. A photo of a birthday cake next to an apple. Yeah, so let's move ahead. Yeah, this is another paper, instruct picks 2 picks. So learning to follow image editing instructions. So now what they claim, I mean they kind of look very similar in what they are doing, but they say that can it follow instructions basically. Okay, so yeah. So what would it look like if it was snowing, let's say, the bottom figure, right? The same image now, similar to what we have seen. So basically for the same image, can you change according to the text, right? So basically you're giving some additional instruction on the given image. So add fireworks to the sky. So it's doing that. Okay. So all this is, yeah. So for example, this is one of their results. How they exactly do, I would request that you may look at the paper. But these kind of things they can do. Okay. Turn her into a snake lady. So it's like the way it's doing that. So yeah, you can have a look at. They seem to be generating like pair of images here, and they use both. I don't know the details. Personalization with diffusion model. So there is another paper, Dream Booth, it came in 2023. So what it does is that given a set of images, it kind of extrapolates to some different environment. So in let's say in Arcopolis here, so you put the how the dog will look like, if it's swimming, it's sleeping, okay, in a bucket, in a dog house, getting haircut, okay. But you have to do it only from some pictures, okay. Some reference pictures are there, and you are supposed to generate all this for the same dog, okay. And same another example they have, same thing, given some clock and all, how it will look like in different scenarios. So this is the Dream Booth method architecture. Again, we are going to skip these details. These are all kind of engineering thing. There is no real. You pick the paper, read, and usually it's easy. Okay. So these are the results. Input images again from the Dream Booth itself. The bag pictures are there, but now this bag is now shown in different conditions here. Okay. So these are the 4 pictures there. Now it is shown in different ways. The teapot floating in the milk, teapot with milk inside, teapot pouring tea, and so on. Okay, so these are all applications. So text guided view synthesis. Now, given a set of text, you may want to have different view of the image, right? So I want to see the cat from top view, as if I took picture from the top. So this is like the top view. Bottom view, as if I am looking at the cat from the bottom. Back view of the cat. Given a set of images, now I can do artistic form. So Van Gogh, by now you must have seen many times. So so his style of painting was like this, and Michelangelo was we have sculpture. He used to do sculpture kind of thing. If you go to this European museums, you see a lot of his artworks there, and so on. Okay, so basically from couple of images can you generate this. And then sometimes the names are kind of given to be instruct and edit and so on, but it seems like they do something very similar. Okay, so there could be many names and so on, text inversion and things like that. Yeah, so this is text inversion. And then there is also given that there are these, just like large language models, you also have, you can think of these diffusion models trained on very large scale image data, and you want it to be very specific for your type of problem. So that would be fine tuning, and maybe you want to train a smaller scale model, so from large scale model. Okay, so this is done in LLM quite a lot, but now you could do also with diffusion model. So this is called low rank adaptations. So this could be the weight of the original model, which is like very big. Okay, someone might have trained this like at DALI level or stable diffusion level, but then you might adapt this specifically for your task. Maybe you want to develop an app, maybe for barcode detection, something like that. And these models are very powerful in segmentation or colorization or things like that. So can you adapt this to very specific app which runs on a mobile phone, let's say, okay, which has less memory. So all this low rank adaptation is ongoing research. So this is low rank adaptation result, where they show the generation on a I believe on a cartoon type generation they could generate. Okay, and again this is all going to fine tuning results. Again, when you do fine tuning, because there are, if you are using transformer type model, then it's like, should I fine tune all the weights everywhere? Because I have self attention, cross attention, even the input embedding weights are there right where the input is going. So which ones you should touch, and what is worth compressing, right? So there were some papers where they said, okay, mostly it's about cross attention, where it is worth kind of looking at. Okay. So so only fine tuning across cross attention layer, and if you work with these things, there are Python codes where you will have like ways to form a parameter group. So when you're optimizing, you say that these are my regular parameters, these are my parameters that you want to pick. So you run a for loop, and by the tag of the function call, right? So when you call this function, so this is like nn dot self attention, right? nn dot cross attention. So you when you run this, you grab these things and say, okay, these parameters I will put in this tuned parameter group, and these are regular parameter group. Okay, and then you on this is how you separate. Okay, so I have worked a little bit on these things. So once you group this, then your optimizer will kind of only compress these ones that you want. In this case, only cross attention. So yeah, these are again like they do some regularization and so on. I am not really sure about how they regularize these things to prevent overfitting. So these are all I guess, yeah, personalized concepts. Again, like these are all part of the same thing. Given a set of pictures, can you kind of do something else? Okay, so given a set of dog images, can you put a headphone there? Okay, so these are multi-view concepts. So multi-view would be, yeah, like you may want to combine 2 or 3 like this. So you have a set of ports and you have a set of cat, then can you combine the concepts? So then the cat is sitting inside the pot. Okay, so it may generate, next time it may generate a little bit of variation of the pot itself or the cat itself, but can you combine multiple concepts? Okay, like this, you have a chairs and cat, then you may want to put the cat on that specific chair. Okay, so can you do that? So combining concepts. Then there is there are on similar lines. There is this another paper, key log rank 1 editing. They are also doing similar thing. One concept is teddy, another concept is teapot. So can you kind of combine them, both the concepts? You can play with the one concept itself, like teddy dressed like something, teddy dressed in a blue suit, and teddy teapot made of gold, and teapot while painting, things like that. This is one concept, but then can you combine both, right? So it's like teapot and teddy both are being used here and combined. So these are all part of image editing. You usually play around. You start with some interesting idea in the beginning, and then you play around with these things. So this is another one, like T2I adapter. Again, all are very recent. A couple of months ago also some came. So 2022, 2023. So these are all happening for last 2 years. Again, if you look into the adapter one, the idea seems to be very similar to the style again type that we saw. That in this case you have multiple concepts here. You do a linear combination and so on, and then it gets injected into multiple intermediate layers of the denoising diffusion net. Okay, so as you can see, the overall idea is like you kind of combine these concepts. If you want to see a combined generation of these concepts, then you are somehow you got to feed them at each layer somehow, and let the network kind of learn from the condition that you give and things like that. There is a text and clip embedding also there. As you know, clip embedding kind of relates text with images. They are kind of trained like that. So this text will be understood in a good way, which images correspond to which text. So all this, if you do it that way, it can kind of start mixing concepts and so on. Okay, so again, there will be some engineering details that we can skip. So these are the kind of applications. A dog in the shape of a letter A. So you have this concept and the concept and also some text, and it is kind of trying to generate that. You have this concept given, and it's trying to generate this. This one combined with this concept. Now you're trying to mixing two concepts. Then these two gets combined to generate a car like this. This plus some house design plus some person, it gets combined to generate this. Okay, so basically the idea is combining concepts. Okay, And then there is kind of like a control net was proposed. So this is again a bit similar to, you see, the style gun kind of thing that you had. Okay, so your conditions that you gave and so on, they get kind of injected at multiple intermediate blocks. Okay, and let the network kind of make sense of all this. Yeah, so this is how, if you train the diffusion model, then this is how overall loss function will look like. It is also dependent on concepts that you are injecting. Okay, so this is again the example from control net. Again, examples from control net. Again from control net. And then as in after control net, there was GliGen. I don't know if I pronounce well. So they had this additional thing that they could also allow concepts as some regions in the image. So it will be better here. So what they said is like, it could be text, but then you can also specify regions as additional condition, that here and here I mark, here I want a I believe the bee here, and then the flower goes here. So it will kind of generate according to the box that you have. Okay, so it will do those box type condition as well. So box plus text. Okay, the boxes plus text, and it will generate this. Okay, so it can do these additional things. You may specify some regions in the image as well. Okay, so these were the things. One of the paper was like, diffusion model is secretly a zero sort classifier. So diffusion model, we know, is a generative model, right? So it creates artistic images. It can creates also based on some conditions and so on. But can I use this as a classifier? So if I have an input image here of a cat, then can the diffusion model be used? Of course, this will be test data, so no one is telling me whether it's a cat or not. Just it goes in, and then the diffusion model is supposed to predict that it's a cat or not. Now, if it is a conditional diffusion model, then we know that based on the conditions, these cats are generated. So from a random noise and the cat level, I trained the diffusion model to generate cat-like images. Okay, and then dog images, and then with the dog class level, I have trained all the diffusion model like that, class condition 1. But then I'm asking now other way. Now I give you random image and tell me whether it was cat or not. Okay, so as you can see from the diagram, what will happen is that now you take the input image, you add some noise to that, and of course you don't know what is in the image. It goes in, the denoiser will predict what was the noise added to this. So that is epsilon theta, and then the actual noise goes in. Now what you do is that you build a loss function at the end, and you minimize this over all class levels. Okay, so you say that, okay, for this class level, is this the denoiser output that was expected, epsilon theta? If it is not minimized, no, it must be something else. For dog class level, is this the epsilon theta prediction correct? If it's not, then you go for some other one, and so on. So the one for which the prediction of the noise is correct with the actual noise, then you say that is the class. Okay, so you do the argmin C there. So you kind of keep generating this epsilon theta predictions for different class levels, and the one for which it's minimized, that's your prediction. So this is interesting. So what they say is secretly a zero sort classifier. It could be used as a classifier. Obviously, you have to do this for all classes, I guess, because you don't know in advance for which it's minimum. So if the classes are only limited 100,000, okay, so maybe you can do this quickly, this difference calculation. But yeah, so but nevertheless it can be used. And same, I mean, it could be used to kind of enhance the classifier and so on. I'm not going into all these details. So these are the papers these are very recent. Diffusion model itself was recent. It was proposed in 2020, 2021. The DDPM kind of papers came, and last 2 years mostly kind of a lot of editing happened, and the engineering style work has happened. So these are all like VIT used here, transformers used here for multimodal and so on and so on, right? So basically a lot of editing, prompt to prompt, so and all this we have seen. So these are essentially the papers. that that do this engineering kind of work. And then later on are equally important, these fine tuning, okay, because very often these big models will be trained and you may want to adapt it for some specific application. So these fine tunings are kind of equally important, right? You may be working on some very specific task. So, and powerful models are there, open source are there, then why not use those pre-trained one and just do a little bit of extra training. Okay, so I guess these are all. These are all, I guess. So that's all. So this was our final lecture. I may want to continue recording for a couple of classes, but officially, yeah, we end the class here. Okay. So thanks.